So one important reaction we haven't talked about yet is the idea of decarboxylating 1,3-dicarbonyls and using these compounds in synthesis. And the names that you've seen in the book in the alkylation section are the malonic ester and acetoacetic ester synthesis. And these are some really important reactions, and you're going to see them on your homework for Monday. So I want to talk a little bit about them and try to explain why these are important and why these are reactions that people use quite frequently. So the goal when we're doing this is to do an enolate alkylation, but not have to worry about competition with aldol type reactions. So I want to do an enolate alkylation without competition with aldol or Claisen reactions. All right, we've talked about how this can be a problem, and this is one really nice solution to this. So what we would like to be able to do, so an example of what we'd like to be able to do is to take, for example, a carboxylic acid and react it with some sort of alkyl halide, add a base, and do an SN2 reaction. So that we can make that compound, right? If you look at this reaction, there's no way that's going to work because the base is going to pull off the acidic proton, and then you're going to react with that, and you're going to form an ester. So that's really not a useful reaction for us to do, right? And then the other sort of reaction that we'd like to be able to do would be if this were a ketone, and essentially the same reaction conditions, right? So base, do an SN2 reaction, and do the same sort of enolate alkylation. And the problem with this is that if we add a base to acetone or any other generic ketone, we're going to get aldol reactions, right? So the problem with these is that we have competing reactions, right? These things are not synthetically useful. Okay? So what we want are ways around problems like this, right? So the solution are these up here, the malonic ester synthesis and the acetoacetic ester synthesis. So let me just show you what these things look like, and then we'll go through the mechanisms so that it's hopefully pretty clear what's going on. So the malonic ester synthesis that's a malonic ester, and we can react this with base, right? And then we can add an electrophile, say something like benzyl bromide, right? That will give us a nicely alkylated product, right? So that we have formed our carbon-carbon bond, right? And again, we've done our SN2 reaction, right? This is just deprotonation to form the enolate nucleophile, right? And then the real interesting thing about this is now, if you take acid and heat, you end up with a pretty remarkable product. You end up with the product we were talking about up here, right? So we end up in this reaction producing 2 equivalents of ethanol plus 1 equivalent of carbon dioxide, right? So that's a pretty interesting reaction, okay? And we'll talk about what that looks like, the mechanism of that in just a minute. And just to complete the thought, the acetoacetic ester synthesis looks very similar. It's just that you don't have a diester, you have a ketoester, So you start with a compound that looks like that. Do the same thing in terms of adding base, and then you can add whatever electrophile you want. Let's take allyl bromide in this case. Right, and then you can form your SN2 product and do the same reaction here, and you end up forming a product that looks just like this one. All right, so really nice ways to get around this problem. And again, the other things that you produce here is one equivalent of ethanol plus carbon dioxide. All right, so again, very, very useful chemistry. And what I want to spend our time with now is just going through the mechanisms of these reactions so that we understand what's going on. But again, clearly here, this is the sort of stuff we're going to use when we do these in synthesis problems. All right, so this is just the first step of the mechanism for the malonic ester synthesis I drew out previously. So we're just going to take the malonic ester, react it with base. We're going to get 100% of the enolate, because again, there's a huge pKa difference between ethanol, which we produce here, and this dicarbonyl compound. So we're going to get 100% of the enolate, and then we're going to do a very nice SN2 alkylation. Okay, so we can very efficiently make that carbon-carbon bond, right? And so now is where things get interesting when we add acid and heat, right? And it's probably better to write acid, water, and heat, right? So when we do this, right, hopefully we're all comfortable remembering that when you have acid and water and an ester, you're going to turn that into a carboxylic acid, right? So, and this is a useful mechanism for you to draw out. I'm not going to draw it out here, but we should be okay with that reaction, right? So we're just turning an ester into a carboxylic acid. In this case, we're doing it twice, so that we can end up with this diacid, right? And so then the question is, what happens to one of these carbonyls? Because one of those carbonyls has to leave. And I'm just going to redraw to highlight what happens in the mechanism. So if we want to see what happens in this mechanism when we heat this diacid to see what happens, we have to draw it this way, right? And we're going to form that OH bond, right? And so we get a reorganization of electrons in which the carbonyl grabs the proton off the other acid. Those electrons fall in to form carbon dioxide. These electrons come over here. So we end up forming an enol, so that what we end up with is carbon dioxide plus an enol. And then, as we talked about before, and as I know you can draw out, we can do a tautomerization reaction. And if you're not comfortable drawing out the tautomerization reaction, you should draw out the tautomerization mechanism, right? This showed up on exam number 1, and it's critical that you be able to draw out the mechanism for this under acidic conditions, okay? So this is a well-known process, this decarboxylation. It's a well-known common reaction, but only for, so it only happens with 1,3-diacids or 1,3-ketoacids. Essentially what you need is a 1,3-carbonyl acid. All right, you need a carbonyl 2 carbons away from a carboxylic acid, and then you can do decarboxylation, right? And this happens in either acid or base, right? And if we think about what the mechanism would look like for the acetoacetic acid, acetic ester synthesis, right, the one that we had before was this compound, right? If we treat this with acid, water, and heat, we would turn it into that carboxylic acid. Again, we could redraw. And we can do the exact same mechanism that we drew up above. To form the enol and carbon dioxide, and then we could do the tautomerization reaction again, and we end up at the product that we saw before. Right? So the key point is that that last mechanism is exactly the same. Right? We go through this rearrangement of electrons to form carbon dioxide. Right? And the key point is if there's not a carbonyl here in the 3 position to the acid, there's no way that you can do this reaction. So you can't just decarboxylate any carboxylic acid that you want. Right? And then one thing that would be interesting is to see if you could come up with a mechanism for what this decarboxylation looks like in base. Right? So that's something that you should give a try. Right? And again, you can use this chemistry on the problems for Monday, and we'll talk more about it on Monday.